Hello and welcome back to Differential Equation. This is section 3.2 on general solutions of linear equations, meaning that we are going to go to higher order rather than only talking about first and the second order differential equation. Now we can deal with the nth order of the differential equation. So we're going to generalize our talk from the last time. So first order in the first two chapters, and then second order in the chapters 3 and beyond. But we can also take a look at the nth order of the differential equation. So we can immediately jump into existence and uniqueness. And say that suppose that functions p1, p2, all the way through pn, r and f are continuous on open interval I containing point A point A is where your initial condition is. Then given n numbers b0, b1 all the way to bn minus 1, because remember b0 is counted, so n minus 1, that adds to have n total n numbers. The nth order linear equation, the nth order linear equation given by y to the nth derivative plus p1 of x to the yn minus first derivative plus p2 of x y to the n minus second derivative plus dot 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 plus pn y equals f of x. And you can see in this equation your second order was y double prime plus p1, let's say y prime plus p2y equals f, right? So you can see that this equation is for any n, because all that happens here is whatever your highest derivative is, you go minus 1 on each one until you go to this last y term, right? So this is the general case to write any order differential equation has a unique solution on interval I that satisfies the n initial conditions so the number of initial conditions has to be the same as the order of the derivative, the order of the equation. We have seen that we had one initial condition in your order 1, two initial conditions last class, right, because it was second order. Now for the nth order you have to have n conditions. So here is the first initial condition, then you have your second initial condition, and then dot dot dot. This is the nth minus 1 over here of A is equal to Bn n minus 1 again, because that's right. You have the 0 ones right here, so that's n altogether, right? Because you have 1 through n minus 1, and then plus 1 more. That would be the n of them. So this is the standard way to describe the system. Now I'm going to add that the solution, just like last time, is the linear combination of all of your independent solutions. So how many you have? If you have a 7th order differential equation, you will have y1 through y7 with this corresponding constant c, and you need 7 initial conditions, right, to calculate those 7 c's. And solution is going to be the superposition of all of them. And then, in addition to all of this, right, when you have the homogeneous case without the forcing term on the other side, right, which is the one that we can solve somewhat easily, you have your Wronskian to be the matrix of the nth dimension. So Wronskian is going to be, again, the determinant, and this is just insane to compute. So we have your solutions y1, y2, y to the yn, to how many of these you have. Then you have your primes over here, and that goes down, and this needs to be square matrix. So you are going to have y to the n minus first derivative here, n minus 1, and then y n minus 1 to the n. So it has to be a square matrix. So for the 7th order, you have 7 y solutions. You will have 7 rows in a Wronskian matrix. You will take 7 hours to compute that, right, to check the independence of the solutions, and so on. Now, luckily, we understand the way all of this works, so we can quickly figure things out and write the solutions. Then you have the system to solve for all of that to get your C's. So yeah, these problems, if you really want to work them out, and many of them are obviously pointless because application doesn't have derivatives going that high. It can take hour, to do the problem for literally no reason whatsoever. So what we know from before is you take your equation and you factor it into a solution, and then you go and you put all of these things together. So let's take a look at some examples and see if we can work this out. So I'm just going to pick whatever problem, and then try to go through factoring and everything to see if we can get all of this stuff working. So it doesn't really matter which one. Let's do problem 16. Oops. Problem 16, and we'll try to do all of this, right, that we cover. So solve the equation, get the solutions. Do we have initial conditions on 14? Yeah, we do. Get the C's and then get. So it's going to be one problem that will, end the course. The class. Class, lecture. All right, so we have a third derivative, minus 6y second derivative plus 11y first derivative minus 6y equal to 0. So it's a third order equation. I better have 3 initial conditions. So y of 0 is 0, y prime of 0 is 0, and y double prime of 0 is 3. Good. They did give me 3 initial conditions. So now my job is to convert this, what we learned last time, into r cubed minus 6r squared plus 11r minus 6 equals 0. So we said last time that we will learn this, why this works today, but that's going to be in the next lecture. So now we're just using still the conversion as was instructed last time. So we are replacing these derivatives with the r cubed and r squared and so on, wherever they belong, keeping the constant the same way as they are. So just one time, 1, negative 6, 11, and negative 6. 1, negative 6, 11, negative 6. Okay, good. All right, so now we are supposed to factor this somehow, right? And that's going to be the any way you can. Now, for the third order equations, if factoring doesn't work, you are literally doomed, because factoring is the only simple tool that we have to factor polynomials and solve these equations that are polynomial equations. Polynomials tend to be the nastiest equations to solve when you need to when you go over the quadratic, right? In this case, we have cubic, and factoring by grouping is not going to work here. So you are stuck either with using the computers to factor, which is what I'm going to do so we don't waste another hour trying to factor this. The other one is to try and guess a method. If you remember in pre-calc 1, like 10 years ago, you took pre-calc 1, there was that method when you guess a solution using the rational zeros, and then you check and see which one works. All of that is fair game. So you learn, I call it PRS, possible rational zeros, and those are the factors of negative 6 in this case. So PRS, that's pre-calc 1 chapter 2. That's where the skill for factoring is. And the possible rational zeros in this case are plus minus 1, plus minus 2, plus minus 3. So, and plus minus 6, sorry, plus minus 6. So those are the factors of this number divided by 1 in this case. And you literally pick any one of these numbers and see when you plug that number in if it's going to give you 0. So let's say r equals 1, just to be cheap, right? R equals 1. That's going to be 1 minus 6 plus 11 minus, oh, I got it. 0. Yes. Okay. I hit gold over here. So if r equals 1 is a root, then r minus 1 is a factor, and I can use long division. Awesome. So that's going to be r minus 1 divided into r cubed minus 6r squared. So actually this is not that bad. R into r goes r squared time, multiply it back, I get r squared minus r cubed minus r squared. When I subtract this, I will get r is gone over here. I get minus, and the minus will give me a plus, so that's going to be a negative 5r squared plus 11 r minus 6. And that's going to go negative 5r times. So that's going to be negative 5r squared plus 5r. Good. When I subtract now, that's gone. This is a 6r minus 6. Nice. So plus 6. There we go. So this is the leftover polynomial. This leftover polynomial factors easily over r is negative 6, right? So r minus 6 and r plus 1. And I have r equals 1, r equals negative 1, and r equals 6. These are the solutions. So I'm just going to really quickly jump on my desktop here on to Wolfram Alpha to verify this factoring. So factor r cubed minus 6r squared plus 11r minus 6. Let's see what it says. Let's go, let's go. R minus 1, minus 2, minus 3. What? Where did I make a mistake? So they do have the same root of r. Oh, no, r minus 1. I did use r minus 1. That's good. I did use r minus 1. So r squared, r minus 1, that's a negative 5. Oh, I factored it wrong. Yep, I got it. Thank you. That's a negative 5. So it has to be negative 2 and negative 3. Negative 2 and negative 3, because negative times negative gives you positive 6. And then minus 2 plus minus 3 gives you negative 5. Okay, there we go. So 2 and 3. Awesome. So R is 1, 2, 3. And that gives us the solution of C1 e to the, is it t or x? It doesn't matter. T plus C2 e to the 2t plus C3 e to the 3t. This is already your general solution. You factored your, while we switch to R, that's going to be explained in the next lecture. And then we used whatever method to factor. That's a pre-calculus issue. That's not your differential equations issue. Now, the fact that I can't do it, that's a separate problem. So once I figured out my factors that gave me my R's, they were all different, no repeats, right? And because they were all different, then we can just write this equation. Now, I am going to now go and calculate this C1, C2, C3 because, right, we do have initial conditions. Now, for that one, I need to find the first and second derivatives. So this is going to be C1 e to the t plus 2C2 e to the 2t plus 3C3 e to the 3t. When you differentiate, right, these coefficients of t from e will drop down. Right, the basic derivative is a e to the at. So, and then you just have the c kind of pop in there. And the second derivative is the derivative of the first derivative. So we have c1 e to the t plus 4c2 e to the 2t plus 9c3 e to the 3t. And we plug the values in. So the first initial condition, y of 0 equals 0, gives us equation 0 is equal to C1 plus C2 plus C3. Because when all of these t's, when all of the t's are 0, then e to the 0 turns to 1. The second initial condition goes into derivative. And this is where we have that 0 is equal to C1 plus 2C2 plus 3C3. And finally, the last initial condition, if I remember, was equal to 3, right? Yep, equal to 3. So 3 equals C1 plus 4C2 plus 9C3. And there is your 3 by 3 system that you need to solve to get C1, C2, C3 coefficients, and then you can plug those into general solution to come up with a particular solution. Now, I'm going to use the matrix in my calculator to solve this, so I'm not adding, subtracting, and multiplying here for another 30 minutes. So I'm just going to use the matrix of the calculator, and if you don't know how to use that, either learn it on YouTube or do it by hand. It's okay. So we have matrix is supposed to be 3 by 4. So 3 by 4 matrix, let's go. 1, 1, 1, 0. 1, 2, 3, 1, 2, 3, 0. And 1, 4, 9, 3. There we go. Now we do second matrix, math, row reduce echelon form. There we go. And then pick matrix A. The matrix A. The solutions that the calculator gives us is C1 is 3/2, C2 is -3, and C3 is also 3/2. Awesome. So now y equals, we have 3/2 e to the t minus 3e to the 2t plus 3/2 e to the 3t. And this would be your particular solution, and the problem is done. Now, we also have Wronskian to show that these solutions are independent. Remember, when you have a repeat, you have to put that t or x, whatever your independent variable is, you have to multiply that one. So what do I do here? Well, for Wronskian now, to check, I'm going to put my e to the t, e to the 2t, and e to the 3t, and their derivatives in next rows. And then again, a derivative. And this would be your 3 by 3 determinant, the same way you learned it for the cross product in Calc 3. And if you haven't had Calc 3 to learn the determinant for the cross product, and you didn't have linear algebra to learn the 3 by 3 determinant, then you can either learn it on YouTube right through. I mean, I'm going to do the details now. This is the way it's done. But then, you know, you would learn this at some point in life, so you can learn it in this class or learn it in a different class, whatever. The way you do 3 by 3 determinant is when you pick a point, and that eliminates the rest of your row and a column, and then you do the thing from last class for the remaining values. So if I pick e to the t, then I have 2e to the 2t times 9e to the 3t minus 4e to the 2t times 3e to the 3t. So if I pick e to the t, then we have a 2 by 2, and 2 by 2 determinant is what we did last time. So that's the first one. Then you jump to the next one, which is this one. And there is a requirement when you do this one. It again kills row and a column. When you do the second one, there is a minus sign that you have to put. Maybe we can squeeze it in here. Minus e to the 2t. This is usually what kills the grade, because you forget that this is a plus, minus, plus signs when you are picking the top row. So when we do this e to the 2t, then for the remaining 4 we do the shape again. So that's going to be e to the t times 9e to the 3t minus e to the t times 3e to the 3t. So that will be, again, the symbol we studied last time with the 4 that are remaining when you delete row and column. And now you go and you pick the third one. The third one is positive. Again, deletes row and a column. So the 4 that are left plus e to the 3t, and then you have again the same thing. So e to the t times 4e to the 2t minus e to the t times 2e to the 2t. And you just go through this algebra and you're done. So what I have here, 18 minus 12, that's a 6. So 6e to the 5, and the one on the outside, 6t. Red minus. Then what do I have here? I have 9 minus 3, that's a 6e to the 6t again. Because this is a 4, and then plus 2 is 6, and you have a 9 minus 3 is 6, so that's what gets there. And then the last one over here is 4 minus 2 is 2, e to the 3t, and a 3 outside is 6, so 2e to the 6t for the total of 2e to the 6t, which is different than 0, which means it is linearly independent for all of these solutions. Again, all of these calculations that you have seen here become way worse when you have 4th order, 5th order, 13th order, because you have to factor, right? And if you don't have access to computer to factor quickly, then the pre-calculus procedure is going to take some time. Once you obtain all of your factors, if there are no repeats, you are free to write your solution. If there are repeats, you have to use those t's in there. And then you go and if the question on the exam says prove that your solutions are linearly independent, what you see on the screen is work for 3 by 3. Work for 4 by 4 makes this calculation exponentially worse, because for 4 by 4 you have to break a 4 by 4 into 4 3 by 3s, and you have to do this to solve 4 times to solve all 4 3 by 3 matrices, because you saw what happened here, right? You had a 3 by 3 matrix, and that broke down into 1, 2, 3 2 by 2 calculations, right? So a 3 by 3 breaks down into 3 2 by 2s. By that logic, a 4 by 4 calculation will break down into 4 3 by 3s, and then each 3 by 3 would break into this. So you have 12 of these terms in a 4 by 4. So it gets exponentially worse in terms of time and calculation the higher you go. Now, usually we have our Wronskians only on a 2 system, right? 2 equation, it's a second order, or 3, which is what you have seen over here. Now, clearly, from this point on, we can just make this worse, right? We can add a repeat, and if you add a repeat, then some of these in here will be a product rule, which would make more calculations and more terms and more mess, but at the end they all work out. Now, what if you had a repeat, which is something that we also learned last class? So let's say you have a 3rd degree equation or a 7th degree equation, whatever, with a repeat. Let's say your equation was, let's say your equation had r minus 1 cubed, or r minus, let's go r minus 2 cubed equal to 0. Now, what would that be in terms of the equation, right? If you FOIL this, because this is my intended problem that I want to solve, so now I can convert it back into differential equation and pretend that I did the problem forward, right? So what I can do here is I can say this came from, well, I can put this, I can lower this down. So if I am to FOIL this, I will have r cubed minus 3r squared plus 6r minus 8 equals 0. There we go. 2 cubed is 8, and then plus minus, and then coefficients are 1, 3, 3, 1. Yeah, okay, good. So a differential equation to start this problem would look like this. It's very easy to create the problems, obviously, for exams and so on, because I have my intended target, and then I can just quickly write the equation, multiply it out, write the differential equation. I'm not going to do initial conditions. I just want to show the general solution, and then you can go through calculations with initial conditions if you want to know C1 and so on. So when I have this, then my R is 2 with multiplicity 3, if you remember your pre-calc, which means that your solution now is going to be C1 e to the 2t plus C2t e to the 2t plus C3t squared e to the 2t. So you see that there is no t, then linear t, then the quadratic t, because this was always e to the 2t. So as many times as it repeats, you always have to go an extra power on the term that multiplies it. And this would be your general solution. Now, if you are given initial conditions, go differentiate it twice, cough, cough, 2 product rules, right? And then, right, you will have 2 product rules, and then later on you'll have another 4 product rules. So altogether, this would take some time to work it out for C1, 2, and 3. But you can do it, right? You can do it. The question is, are you able to, factor it from algebra and pre-calc and get those R's? Now, you could have, 2 of them repeated and 1 of them to be different. That's possible as well. You can have R, let's say, plus 3 times R minus 1 squared equals 0, right? So this is R equal negative 3 and R equals 1 multiplicity 2. So your solution is y equal C1 e to the negative 3t plus C2 e to the t. Because that's a new type of a solution, there is no need for that t there. It's a different one, right? But now there is a repeat, and this is where t kicks in. Because R1 has the repeat of e to the t, so this extra t pops up only once. So if you sit down and study these things, they will eventually make sense, and these are way quicker to solve than chapter 1 equations, provided you can factor quickly, right? And you can go ahead and figure out what the differential equation is by simply foiling this, then write the R row, and then you write your Y in terms of differential equation. So you can go back and you can create the problems yourself, right? You just say, what is my target? And then you go back steps. This is how we create problems. This is how problems for the book are written, right? You wonder why they all work out to be, in quotation marks, nice numbers. Well, we know what we want and we just work it out going back. This would be R plus 3 times R squared minus 2R plus 1. And when you now FOIL that, that would give you R equation, and then you can just write the Y equation, replacing those R's with Y primes. So you can go back and figure it out. That is, believe it or not, that is your 3.2 higher order behaves exactly the same way as the first and the second order linear equations. And for the constant coefficient ones, we can convert those to r's and then factor somehow. And well, there's still one more case that we are going to cover when we come back to class. And that case is when you guys have complex roots with i's, and then we want to know how that works out. So we'll see that when we come back. But that's it for the higher order equations, and especially the ones with constant coefficients. Bye.